Okay. Now, we actually don't much need y2 because what it gives us, if I've even said this correctly, and I think I have, but I haven't proven it, okay? So we need to verify it. We'll see if it's consistent. What we really have is this solution, okay? So y1 equals, if I multiply through here, it equals e to the t cosine t plus I sine t, and I times this, right? So I guess I'll write out the details. I e to the t times cosine t plus I sine. Okay? And that equals e to the t cosine t plus I sine t e to the t times negative sine t plus I cosine t. Just multiplying through by the I. Okay? Which equals e to the t cosine t e to the t sine t plus I times e to the t sine t negative, and this should be negative, sorry, this is positive, e to the t cosine t. Okay? Now, this column vector here solves the original equation. Okay?
Not the other one?
I haven't mentioned it yet. I'm sticking to the fact that this solves it. Because, of course, when I plug this into the original equation, which has all real coefficients, everything stays real, and the solution has to equal 0. Okay? Which means that what we get from this solution is the real part of something that equals 0. So it has to be 0. Okay? But of course, the imaginary part also has to give us 0.
Would it
I
be,
can say, well, so is this.
would it be any combination of two?
Well, any combination of the two is, and this should be a combination of those two. So we really don't need this. Okay? And I'm not even sure I spoke correctly with this, so I'm going to put a big question mark around this thing. Because there are little details of the complex arithmetic that I can't reliably do in my head and hadn't thought through because I didn't know what we were going to do today. Okay? Depending on what questions you had. Since you didn't have any, you see what happens. Okay? Okay, now let's see if everything there is on camera we can be read. I don't think we can necessarily read all the word this, but I think everything else is pretty clear. Move this over just a minute. This one won't go. You can see that Y. Okay, there we are. Okay? So now we have two solutions. So our solution set is e to the t cosine t negative e to the t sine t, and e to the t sine t, e to the t cosine t, or any linear combination.
What about I?
Any linear combination. Meaning I could use this one plus I times this one. Because now we're in the complex field.
That doesn't seem fair.
It is. And it totally simplifies a whole huge amount of engineering, as you will see. Okay? At a certain point, almost all physics and almost all engineering is done in the field of complex variables. Okay? Of course, if you really like that, there's also one of those electives that you have to take, you have to choose from, that introduces you to the deeper theory of functions of complex variable. It's only a surface introduction to the thing, but you get some pretty powerful techniques. As somebody whose field was functions of a complex variable, I can say you get a pretty powerful but very limited picture of the field. Just the part that directly applies to most engineering. All the rest of the field, a lot of it does apply, but it gets pretty deep. And it had pretty much all been figured out 150 years ago.
How did they come up with all these functions? I get how they come up with polynomials, but how did they come up with trigonometric functions? Who would have thought of such a thing?
The ancient Egyptians had them, so they've been around longer than most of the other stuff, way longer than calculus. Okay. Also, if you're trying to model a sine wave, it comes up naturally. You generate electricity with an armature rotating at a constant speed in a magnetic field. Okay? So, those functions have been around for hundreds of years. Okay?
What about, I guess exponential would have been.
That's pretty natural too.
Yeah.
Yeah, you start charging compound interest. But, or you look at population dynamics, all kinds of things. This stuff has been around for hundreds of years, okay?
Well, it's just fun.
Most of what you are learning has been around since the 1700s.
Yeah.
And much of it much earlier than that. It was late 1600s when calculus was developed.
It got stitched together in the 16 and 1700s. Right?
Yeah, it was all put on a rigorous foundation in the late 1800s and early 1900s, okay? So nobody really knew why it worked, they just knew that it worked. And that's all very interesting, but not all that relevant to an engineer. So if you're interested in it, you can learn about it. And I certainly recommend it because it kind of deepens your understanding.